Here we are looking at the warm-up from our 2.1 number 2 set of notes. We're asked, given the following position versus time graph with the function, here it is, find the following secant slopes. Now, again, here's our graph, and it is a position versus time image. So in other words, what that means is our x-axis is our time, and our position is going to be represented as s of t. Which is pretty much your y-axis. So as time goes on and lapses, our position for this particle actually just kind of moves. So this particle could be anything, though. But again, that's kind of just what the different variables are actually standing for, time and position for this particle. Now, when we're looking and finding the secant slopes, we notice that we have this particular t-value 1 and this other t-value 2. And again, what these are pretty much are just your considered x values. But what we have to find are the corresponding y values along with them, or our s of t's. So all we have to do then is plug in our different t values and see what they come out to be. So at s of 1, in other words, when our time is 1, and we throw him in there, he comes out to actually be 4. When we throw in 2 into this function, we end up, in fact, let's just go ahead and do this one so you can see it. We have negative 2 squared plus 4 times 2 plus 1. This comes out to be 4, negative 4, plus 8 plus 1. So then it looks like 4, 5. So the position at time 2 comes out to be 5. Now again, we're looking for the slope of these secants. So we're just pretty much finding the slope between these 2 points. So here's one point, 2 comma 5, and our other point is 1 comma 4. Well, we just basically find slope like you normally have. So you have 5 minus 4 over 2 minus 1. And again, this is the secant slope, which just comes out to be 1 over 1, which again is just 1. And pretty much what that's saying is at this t-value 1, comma 4, and this t-value 2, comma 5, we found the secant slope between these 2 points. All right. For the next one, we're looking at t is equal to 1, and then t is equal to 1.1. Well, we've already gone ahead and found this y value, so we don't have to worry about him. Going ahead and finding the position for 1.1, when we throw that into the function, it does come out to be 4.19. You just throw that into the calculator. So then to find the slope of that secant, we have 4.19 minus 4 all over 1.1 minus 1, which comes out to be 0.19 over 0.1, and as a result, the slope of that secant comes out to be about 1.9. Getting even closer to this target t of 1. Again, we know that it is already 1, 4. Going ahead and getting closer to this target point 1, by using the point 1.01 and throwing that into our position function, we end up with the y value coming out to be 4.019. So then to find that secant, we have 4.019 minus 4 all over 1.01 minus 1, which comes out to be 0.019 over 0.01, which comes out to be about 1.99. So it looks like the slope, particularly at 1, in other words, at 1.1, we saw that slope going through those 2 points. And then finally, at 1.01, so almost on top of 1, we saw a slope that was pretty much dead on with the tangent, not quite tangent, it's still a secant there, of 1.99. So almost 2 though. It's looking like this thing's probably going to be approaching a slope of 2, a tangent slope of 2. Now the secant lines that we're finding actually represent something in terms of real applications. What they actually represent are the average velocities of things. And the tangent line, those represent our instantaneous velocities. And you can even see that, like, between this green, these 2 points, we could actually see the average rate of change, which is, again, pretty much what a slope is. For this red one, it's a little hard to see, but that was an average rate of change. It was just very, very close to that target point. The black represented pretty much almost an instantaneous rate of change at that particular point. So again, secants represent average rates of change, in this case over time for a particle. And then as you get closer and closer to that tangent, you're getting closer and closer to the true velocity at that particular point. All right. So again, when we were finding all these secants, these were average rates of change. So the average. This guy was a average velocity. This one was still a average velocity, but he's borderline getting there to be close to that instantaneous rate. So that tangent. So again, though, that is the warm-up from our 2.1 number 2 set of notes.